Hi everyone, so this is the second lesson for chapter 9. We will be looking at resistance. So I'll go through the quick checklist here. We'll be looking at resistance, the equation for resistance, which you have to recall, so you can add it to your formula booklet that I gave you as well. It's something that you have to remember. It's only a couple of equations you have to remember, so it's not that many, and it's one of the most basic ones. You should be able to state Ohm's law fully, and we're going to come to it, and I'll explain what I mean by that. Then we're going to look at the IV characteristic curves for a resistor, filament lamp, thermistor diode, and a light emitting diode, so LED. They're very important to know. They all get tested in exams, and they're quite simple things actually. Then also you need to know techniques and procedures that you use to investigate these characteristics for ohmic and non-ohmic components. So I'll get to that, what that means. And also you need to know how light-dependent resistor varies with its light intensity. You also need, in this part of the topic that I'll go through, sorry, you do need a lot of practical skills. So I will talk through it in the video. Do make sure you take notes. Well, obviously I will put it in the questions that I will include in the homework. But the very important skills that you need to be able to use to describe what's going on. So to begin with, we're going to have a look at resistance and what that means. So we have every component that we have in a circuit, including the wires, have resistance. So resistance you can consider as something that resists the flow of charge carriers. So in the case of circuits, the charge carriers are electrons. So we're talking about in circuits, they're electrons. It is defined as the ratio between potential difference and current. So R is equal to V divided by I, where R stands for resistance. Resistance is measured in ohms. It's a capital omega. Sorry, I didn't write that very well. So it's a capital Greek letter omega. It's like a head with no neck and the shoulders. Then you have potential difference, which is measured in volts, and you have current, which is always measured in amps. Any other units need to be converted to this basic unit. Well, they're not basic units, but they are the ones that are used in the equation. You also need to know the definition of the unit ohm, just like we talked about knowing the definitions of potential difference, of current, amps, voltage, amps, and coulombs. You need to know the definition of ohm. So the ohm is defined as the resistance of a component when the 1 volt is produced per ampere. So you have 1 volt per 1 ampere, or 1 ohm is equal to 1 volt to the minus 1. Now, this was discovered by a German physicist Ohm at the time, like actually quite a while ago. I think it was the 1800s. He basically investigated how what would happen if he doubled the potential difference by adding more cells. And he realized that the current doubled as well. So he came up with the idea that if potential difference is directly proportional to current, then there should be a constant. And that constant for that wire specifically was the resistance. And then the same connection was made for other components. Okay, so a very simple way of investigating this relationship is starting with a single cell, adding a wire between 2 points, so just a little wire. You obviously need to be able to measure current, and to do that you need an ammeter in series. You also need a potential difference across the ends of the wire. To be able to get different values for potential difference and current, you have to obviously keep changing the number of cells, so you can add more and more cells individually, and take the readings of the ammeter and the voltmeter to get the resistance across the thin wire. So you could plot easily current against voltage. This would normally lead to, if you have zero current, obviously you have zero voltage, and that will lead to a straight line going through the origin. That will mean that the gradient of this line, so if I get the changing y over the changing x, it will be current over voltage. We know that the resistance is V over I, so the gradient, in other words, will be 1 over R. Because you have to rearrange the equation. So the gradient will be equal to 1 over R. If I compared what the gradient gives me in terms of the axis labels and what the equation gives me, I can link it together to get the gradient in terms of R. So we're going to have a look now at Ohm's Law. So we discussed how resistance can be calculated and how the unit ohm works. Just a quick note about the unit ohm. So if I say the device has 500 ohms resistance, that will mean that for 500 volts, for example, 500 volts are a component. If there was a component that had 500 ohms of resistance, that will mean that a potential difference of 500 volts, there will be a potential difference of 500 volts when there is 1 amp of current in it. So that's basically using the equation again of what it gives you. We also saw the equation, its units, and we're going to have a look at Ohm's law now. Now, Ohm stated that for a metallic conductor that's kept at a constant temperature, so like a wire basically, and it's metallic is very important because we do use components that have semiconductors inside of them. So for a wire kept at a constant temperature, the current in the wire is directly proportional to the potential difference across its ends. Or in simpler words, current is directly proportional to the potential difference across the component's ends when temperature is constant. Now, many people tend to forget this part, that Ohm's law is current is directly proportional to potential difference. They remember that, but they always forget that is when the temperature is constant, and that usually costs you the whole mark in the exams. Now, what does that mean? If something is directly proportional, if I double one side, then the other side has to double. So if I double the potential difference, then the current should also double. Now, why are we saying constant temperature? Why does this happen only when there's constant temperature? Well, when you tend to heat up, when you have components in a circuit, they start heating up, and that's because of the resistance through them. I will explain it in a second now, but the idea is, why would something heat up? So if you go back to the first, one of the few first lessons of chapter 8, I think, when I explained how inside a wire you have the positive nuclei that are fixed in their position, and then you have the delocalized electrons that are free to move, then it will make a little bit more sense, and I'll go to it in a second. So we know that current is the flow of electrons in a wire. It's different, it's the flow of charge carriers, but in the wire is the flow of electrons. So if we consider that, obviously, anything that has energy vibrates, including internally in our body, everything is vibrating, all of the molecules are vibrating at all times. Now, if I pass a current through it, these electrons will keep pumping around, moving in a haphazard way, constantly. And these collisions, if you start playing with basketball and you keep bouncing on the floor, eventually it will feel hot to the touch. So that friction, those collisions cause heat, and the wire eventually starts heating up. And the more it heats up, the more energy goes to the positive ions, which makes them vibrate more. The more they vibrate, the harder it is for electrons to pass through them, which means there's going to be more frequent collisions, which leads to a higher temperature, and so on and so forth. So just to summarize in a nice way, when you have an increase in temperature, the ions have more energy, so the positive ions here. They vibrate more from where they are fixed, and that will mean that there's more frequent collisions between the positive ions and the electrons. And the electrons will end up transferring more energy in order to go through the wire or through the component, and that's why resistance increases when you have temperature increase. This is an important explanation. If you don't understand it, do please let me know. I might try and model it in class or something. But you can even consider it as you going to an obstacle course and you have all these barriers that you have to walk through, and they're moving a lot. They're just vibrating around their fixed position. So if this is their fixed position, they're just vibrating around, and you have to pass through them while other people are trying to pass through them. What will end up if they start vibrating faster is that you will end up colliding more with them and other people, and that will lead to you needing more energy. You'll feel more exhausted at the end of it trying to get through an obstacle course as well. So it's quite similar to what happens with electrons in a wire. So we kind of spoke about Ohm's law, and we explained why the temperature being constant is very, very important. You could actually investigate this as well. So I'll describe quickly how we can investigate it. We can do something similar that we spoke about at the beginning with the just investigating resistance. So you could get another wire and just put it in a bundle there. And you can start recording the current with time. You will end up with a graph that is current against time. It will look something like this. Now, as time goes by, the current through this wire, this bundle of wire, is decreasing. Now, we know that the potential difference is the same. Well, the EMF actually, but the potential difference, let's assume that there's no energy loss, so the potential difference will be 1.5 volts. So if the potential difference across it remains the same, that means I have V is equal to IR. So this is a constant number. Now if current is decreasing, that means the resistance is increasing. That means the electrons are now needing much more energy from the from the EMF to pass through the component that they did before, because the temperature is increasing as time goes by. That's why usually it's good to have a switch when you do experiments, and open the switch between readings to allow the wire to cool down back to the room temperature, to make sure that the temperature is not taking effect in your experiment. So current and potential difference are not the only two things that can actually increase the resistance of a component or a wire. Especially for wires, there's other things. So like some metals contain, so the material is important. So another factor that can affect is the material, because some materials have more electrons that are free to move, so delocalized electrons, which will mean it will be better conductor, so the resistance of that will be lower. The length of the wire is another factor. So if you want to view it in this way, so if you have a longer path for electrons to pass through, that means there's going to be more collisions compared to a shorter length wire. If there's a longer length wire with more collisions, that will mean that they require more energy per unit length to be given away. So if you have more and more collisions going through a longer wire, that will mean that your resistance increases. So longer wires have larger resistance. And then we have the cross-sectional area of the wire. That's important. This is quite similar to what we said before. By increasing the cross-sectional area of the wire, it's much more like having a number of wires bundled together. If there is no increase in potential difference, that will mean that there are more electrons available to flow. So if you just increase the cross-sectional area compared to a smaller area of the wire, you have more free electrons. But if the length, assuming that the length of the wire remains the same. So you have more electrons, that means more free charge carriers. So the bigger the area, cross-sectional area, the lower the resistance. And as we already mentioned, the temperature as well has to do a lot with the resistance. So the higher the temperature, the higher the resistance. However, this only applies to certain components. Some components are actually not part of this, especially thermistors that we're going to talk about later in this video. So the next thing that we're going to look at is the IV characteristics of resistor, filament lamp, thermistor diode, and light emitting diode. To start with, what is an IV characteristic? It's basically how current and potential difference for any component, so the ones that are mentioned in here, shows how the relationship between electric current in a component and the potential difference across it behave. So it's the current, potential difference characteristics of a component. So the first one we'll have a look at is a resistor. Now resistors are designed in such a way that we need to ensure that the resistance is constant. It might vary by a tiny amount, but it should be constant, even if there are like tiny variations in temperature. So in a resistor, if we want to investigate a resistor, for example, we can place a power supply. Actually, let me just draw a power supply. Connect it to an ammeter. So if I want to know the IV characteristics, obviously current, I need the current, and I use an ammeter for it. Then I can place my resistor, a variable resistor, because we need to be able to collect a lot of values for current and potential difference, and the only way to do that is by adjusting the resistance in the circuit. So the variable resistor does that. And obviously our component needs a potential a voltmeter to measure the potential difference across it. If we record the results for this, we will get a graph of IV that looks like this. So a straight line going through the origin. Now this shows that the current doubles as potential difference doubles, and basically it just shows direct proportionality between current and potential difference. We call these type of components ohmic conductors. So that's what we meant by ohmic conductors before, because it follows Ohm's law, so it obeys Ohm's law. So that means that the resistance is constant. So these are the important parts of this. And even if I change the polarity of the power supply, so to get positive values, you need to make sure that the ammeter and the voltmeter read positive values. And when you reverse the polarity of the power supply, then you'll be able to get the negative values of current and potential difference. So this is how most wires and metallic conductors behave, just like the resistors. And then we have filament lamps, which we're going to look at. So I spoke already about one method that we can use to investigate resistors, so by connecting it in this way, by connecting a variable resistor. But there's also another way of investigating the resistance of a component, which I will explain in later videos why we can do it in that way when we start learning a bit more about how resistance is split in series and parallel circuits. For now, just remember that there are two ways, and I will explain it later on when we start learning more about resistance in other circuits. So this is a potentiometer setup. So this part is what we're interested in. This is a sliding arrow. So this is a wire that slides across the length of a rolled wire. We'll explain that, like I said, more when we reach that part in the chapter. I think it's the next chapter, if I'm not wrong. But remember that this has a little bit more development and is coming in the next chapter. So yeah, it's quite a similar setup. The ammeter is in series with the component and the voltmeter is in parallel. Now if I do my experiment and I record the current and voltage by changing the resistance through the potentiometer, then I can get my IV characteristic curve for a filament bulb, and it will look like this. Now remember, again, you need to reverse the polarity of the battery to get the negative values. So if we look at the graph, there's a few conclusions that we can get from it. So for a very small amount, so between this point and this point, the potential difference and current are quite a bit proportional to each other. But then as the voltage increases, the potential difference, across the filament lamp increases, the current doesn't increase at the same rate. So if I double the potential difference, the current doesn't double, which means that the filament lamp does not obey Ohm's law. So we say that this is a non-ohmic component. And to remind you, filament light bulbs, so this is a filament bulb, they have a metal wire in them. So as we already said at the very beginning, the first half of this video, if you have a metallic wire or any wire in general, as time goes by, the temperature increases, which means the resistance increases because you have more collisions and so on. So it has non-ohmic component, which means the resistance of the filament lamp is not constant. So resistance is not constant because the temperature changes. So the filament lamp behaves like that when no matter what the polarity of the battery is. So it's a very important part of our determination of what's going on actually there. So that was just it for filament lamp. We need to go on to the diode now. So I did already mention what diodes do. They only let current. So through one direction. And diodes are actually very, very important in our modern technology. You don't see them very often, but they're everywhere. They're in mobile phones, cars, washing machines, phones. We said in a lot of components. Your laptops, and the reason is very, very important part in our lives. So a light bulb is different from an LED, a light emitting diode, because wherever way you connect the light bulb, it will work. Whether you connect it positive to negative, negative to positive, doesn't matter. But diodes and LEDs don't do that. They just simply won't work if you connect them in the wrong direction. We did mention this in the first lesson as well of chapter 9, that you need to connect them in a specific way. And in the diagrams, you always have to show them connected from positive to negative. Some diodes are actually made from a material that emits light when it can conduct only. And LEDs especially always emit light, well, most LEDs emit light of a specific wavelength. So that will be useful later on when we look at quantum physics. So let's talk about the IV characteristics. So if I connected my circuit in this way, by the way, you always need a resistance in when you connect a diode or an LED. So you need a resistor to protect it from burning out because too much current through it affects it. So we can connect our circuit in this way. So if it's an LED or a diode, so let's say this is a diode. And for an LED, remember the symbol is like this. Sometimes you'll see them drawn with a circle around them. It's the same thing. And when we plot it and get the results in this setup, we'll get a graph that looks like this. Now, why is this section 0? So current is 0 in the negative potential difference. For example, that's because if you connect the cell the other way around, current is not allowed to go through it. So that's already one of the features that's very, very important. So when you look at this graph, you can already see it's not a straight line going through the origin. So that means that this is that potential difference is not directly proportional to current, which means it doesn't obey Ohm's law. So if it doesn't obey Ohm's law, we call it a non-ohmic component. And that means that the resistance is not constant. And also that the LED or diode's behavior depends on polarity. Polarity is whether it's positive or negative and positive. So it's just switching around the terminals of a battery. So you can see that in this section, there is infinite resistance, okay? Because the current obviously is 0, so there's a lot of resistance, very, very high resistance. When the potential difference is reversed, then the diode will conduct, but it will only start conducting at a specific potential difference. That's usually, I think, about 0.7 volts, if I'm not wrong. I could be wrong on that, but usually it's at 0.7 volts. Basically, if that's just about when we start having current through the diode or LED, and as potential difference increase, the current increases, which means that if current increases, the resistance decreases because it allows more current through. We said already, the higher the resistance, the lower the current. So yeah, the resistance actually drops extremely fast for very small increases in potential difference, and we say that at this point it has little resistance because it increases very sharply. But obviously, like I said, this is a rough value, especially for LEDs. They have different threshold potential difference. So we call this a threshold potential difference, meaning that's just when about the LED or diode start allowing current to flow through a specific potential difference. So different LEDs, for example, red will start at different potential difference, letting current through. Green will start at a different value, and so on. And we will come back to this again when we do quantum physics. So that's we already seen the resistor, the filament, lamp, diode, and LEDs, and we need to talk about the thermistor now. Okay, so what is a thermistor? Now, thermistors are temperature sensing components. They change their resistance. They're basically resistors that respond to heat. But the idea of a thermistor is that we have a different response from it because it has a semiconducting material. So some semiconducting materials, some semiconductors have a different ability to metallic components. When you heat them up, so in a thermistor, the semiconducting material used behaves differently when you heat it up. So if you heat it up, it releases more, the number density increases. So remember, number density is the number of free charge carriers per unit volume. So when you heat a semiconducting material, which a thermistor is made from, the number density increases. Number density, we've seen it in chapter 8. So remember, it's the number of free charge carriers, which means we have more, the number of electrons actually increases. And we know that if there's more electrons, that means the current should be higher. So current increases, which means that the resistance will be decreasing. So the higher the temperature, so this is at high temperatures. At high temperatures, the resistance decreases. At low temperatures, the resistance increases because there's not as many free charge carriers. So just to quickly summarize, at high temperature, number density increases, which means more free electrons, which means higher current, which means lower resistance. So we're going to have a bit of a talk quickly through how we can investigate this. So you can place a thermistor in a bit of water. It could be a water bath, because a water bath avoids you having to heat it with a Bunsen burner, which is a bit more dangerous. So water bath, you simply place water in there and you can change the temperature and adjust and just wait for the equipment to get to the same temperature. You have a thermometer, an ammeter and a voltmeter to record the potential difference and current, which can be used to calculate the resistance for different temperatures. Once you get that done, and also just to ensure a few bits and pieces are correct here, the water bath is used for changing temperature. So instead of using a Bunsen burner, which could expose your wires, which could overheat it, which you actually not lose energy, but it changes the temperature quite quickly. With a water bath, you can change the temperature slowly and wait for the equipment to adjust to it. You also need to ensure that you stir around the liquid so the temperature is even. So by just using a little stirrer, so just stir through it to make sure the temperature is even. Ammeter and voltmeter is just to measure the resistance across different temperatures. And when you do draw your results, then you will notice that the graph looks like, so for resistance against temperature, the graph will look like this. So at a very low temperature, you will have high resistance, but as the temperature increases, the resistance drops. So this is one practical that you should know how to conduct. You should know how to make it more accurate, and so on. Now going to the characteristics, the IV characteristic curve. So what we have for a thermistor looks a little bit similar to a light bulb, filament lamp. However, there's one very major difference. Here we see that as potential difference increases, current increases at both polarities. That means that unlike the filament lamp, so obviously this is not a straight line, so to make things first simpler, potential difference is not directly proportional to current. It's a non-ohmic component, since it doesn't follow Ohm's law. The potential difference is not directly proportional to current, so that's the Ohm's law. What we can see here is as potential difference increases, current increases, which means resistance decreases. This is the major difference between a thermistor and a filament lamp. In the filament lamp, we saw this shape, which meant that there was less current for each increase in potential difference. And we already mentioned that in a thermistor, as temperature increases, which it does increase, there are more free charge carriers, which means more current, which means lower resistance. So these explanations are very important to this topic. It's quite a simple topic, but the explanations have and the key terms and the key values that you see in graphs, current, voltage, resistance, they're all linked together and they're very, very important. So we kind of have spoken about these two parts. I will leave this for the next video because it's getting a bit too long, the video, and we'll discuss this in, well, if you have any questions for this, we will discuss this in class. So we'll leave part D for the next video.